Hello, Legacy Sabers. Marsh here. So today we're going to talk about a special kind of program creation or program methodology called recursion. Our essential question today is, how do I deal with a function that calls itself? So a function that literally has in itself a call to itself. It's kind of an odd idea. But ultimately, so far, we have seen methods that call other functions. For example, we've seen the main method call the square function, or in a class, we've had a function that called another function that was in the class as well. A recursive method is a method that is calling itself. So, for example, my function compute could call itself once more to find out more information. This is definitely a different kind of program and how it runs. A recursive method solves some problems. A lot of times what you're going to find is the code of the recursive method should be written to handle the problem in one of two ways. So usually there's an if statement written in a recursive method. The first part is the base case, which is the simple case of the problem that can be answered directly, and you do not use recursion in that one. And then the recursive case is the more complicated version of the program that isn't easy to answer directly, but you can express it elegantly with recursion. So you make a recursive call to help compute the overall answer. We'll take a look at a program here in a little bit. So why use recursive methods? Well, in computer science, some problems are more easily solved by using the recursive functions. A lot of times, the Towers of Hanoi is a very common one, or perhaps factorial is another one that we'll take a look at. Those are more of the common ones that you get to see that a recursive method or a recursive solution works a lot better. If you go on to take other computer science algorithm courses, you're going to see lots of examples of this. Another thing, the idea of traversing through a directory or file system. So the idea of I got to click through all of the folders until I hit a folder that has nothing in it, and then I can go back up. Or traversing through a tree of search results. Today, we're just going to focus on basic structures. We're not actually going to write them just because it is an introduction to recursion. So, the world's simplest recursion program. So we got our program called Recursion that has a method called count. Count requires a int variable, an int parameter to be sent to it. And we have right here, notice down here, we're calling count the same function again. So that is where that recursion is going to occur, because you're going to see that the count function can call itself. Okay, to understand how this thing works, we're going to help to visualize what's going on. We're going to do something called a stack. A stack is a data structure that is used to store the method calls in the order in which they are created. So as you create a method call, it goes on the stack. A stack is basically operating like a container of trays in a cafeteria. It only has two operations. You can push something onto the stack, and you can pop something off the top of the stack when we're looking at it. When you run a program, the computer creates a stack for you. Each time a method is called, the method is pushed onto the top of the stack. And then when you finish a method or it returns something, the method is popped off. A lot of people call this a last in, first out function because as you put things on, the last thing that you put in to the stack pops off first. Okay, and we're going to take a look. We're going to draw a lot of stacks here in a minute. So we have a simple program right here. So the program starts, there's an empty stack. We start the main method. The main method calls the function square, so we have to push the main, and then we push square off onto the stack as well. Square returns a value. It pops off because it's done doing its job, and then the main pops off because it's done as well, leaving us with an empty stack all the way at the end as this information that we're looking at. Now, what if the method doesn't finish before another method is called? So for example, what if square called another function or another method? Well, in that case, a method that calls itself recursively, we just push another copy of the method onto the stack. Each method must pop off the stack before the next method can even finish. So what you're going to see is a lot of times we're going to be pushing the same method over and over and over and over and over onto the stack until one of them finally can finish. So we're going to go back to our very simple recursion program. And we're going to visualize this recursion. So first thing that happens on this stack, so here's my stack. Okay. First thing that's happening is we are calling the main function, right? Main calls count with a spot of 0. So now I'm going to go down here. So count is 0. So I'm going to print over here index. So over here is what I'm printing. This is my printout. So I'm printing index. So count sent a 0 first. If 0 is less than 2, I need to count 0 plus 1. So now onto the stack, I need to put count 0 plus 1, which is a 1. Now notice count 0 is not off the stack because I haven't technically finished. Count 1 has to finish before count 0 can actually get off the stack. So now I'm going to call the count function again with a 1 inside. I'm going to print my 1, and I'm going to check, is 1 less than 2? Yes. So I need to call count again, but this time a parameter of 2. So now I'm going to check, print my 2. Is 2 less than 2? No. I can stop, right? So I've reached the end of my function, my method count 2. So that guy's going to pop off the stack. Now count 1. Since count 2 finished, count 1 can reach the end, so count 1 pops off the stack. Since count 1 finished, count 0 can pop off the stack. And now since I have gotten to the point, and actually I just realized that was a print line, wasn't it? So it'd be 0, 1, 2. It would look like that. Since I've run to the end, main, I'm going to go to a new line, so I'd be right there, ready to go again. And main would pop off the stack. Okay, kind of different, right? You got to almost visualize what are you doing? When can this guy contently be quote unquote done? When can I pop it off the stack? So we're going to do another program here. Same one, different numbers. So I'm going to visualize my stack. Here's my stack. I'm going to make myself a big stack so I have room. And then this is my print lines. So this is what we're going to be printing. So first thing on the stack, main. Okay, count 3 goes. Okay, so down here, we print out a 3. Is 3 less than 2? No. So I go count 3, goes off the stack, go back up, new line, main goes off the stack. So see, I didn't even recursively do anything because there was no recursion to happen. 3 was too much for the recursion to be called. So I've reached the base case is what we normally call that. So let's try another example. I have recursion starting right there with that up and down. So we need a stack. So let's go ahead and make ourselves a stack here. So first thing, main, obviously, is called. Over here, we're going to need a print line. So we're going to do some prints over here. Okay, so first thing, I see up and down, 1 was called. Okay, so 1 is here. So we're going to print on a new line, level, my n is 1. Okay, if n is less than 4, yes it is. We're going to call up and down n plus 1. So I got to go right here, up and down. So we did 2. So I'm going to go back in here. So I'm going to go to a new line. I'm going to print level 2. Okay. Now is 2 less than 4? Yes. So I have to go 2 plus 1. So up and down 3. I need to go in there again. Level 3. Is 3 less than 4? Yes, it is. So I gotta call again. Up and down 4 is what I gotta call now. So I got level 4 to print. Is 4 less than 4? No. So I get to finally go to this system out print. Notice we've never gotten there because we literally have been recursively calling. So now I get to go to a new line. I'm running out of room over here. Now it's all capital letters. Level 4. Now I've reached the end. So level up and down 4 can pop off the stack. Now, since 4 finished, I now can finally get here. And right now on the top of the stack is a 3. So I can use 3. He's reached the end. He can pop off the stack. I then need to do 2. So it can pop off the stack. I need to now do 1. So it can pop off the stack. And since I finally finished up and down, I can go to the main, which would give me a new line, and main can pop off the stack. So I print level 1, level 2, level 3, level 4, level 4, level 3, level 2, level 1. Kind of different, right? You have to a lot of tracking. This is one of those ones that you cannot kind of keep in mind. You actually have to write stuff down so you're able to track it all. Why would you use this? Well, iteration, you can use repetition structures, for, while, do while, repetition through explicit use of repetition structures. A lot of times you can terminate, controls repetition by using a counter. Recursion, usually you're using selection structures. So if else, switch statements. You're repeatedly calling method calls. Controls repetition by dividing problem into a simpler one. A lot of times you'll see most programs can be written with iteration or recursion. Some people's brains just really work in recursion. Some people's brains don't. However, there are algorithms that recursively, they are much easier to write. So it depends. Both of them are usually writable. It just depends. One of them might be easier than the other. Recursion does have more overhead than iteration. It's also more memory intensive. That stack really does hold a lot. Often, recursion can be also implemented with only a few lines of code. Iteration, you might need a lot more to do that. So let's trace some recursion methods here. So I got first mystery 6, 13. So that means I'm going to go in here. Is 6 less than 13? Yes. So I'm going to return my X, which is 6. That one didn't call didn't do a stack, so I don't have to worry about that. 14 and 10. So 14, 10. Is 14 less than 10? No. So I now need to return. Look, we got to do got a stack to start here. So I'm going to go 14 minus 10. That is 4. So I'm going to go M 4, 10, right? Is what I popped onto the stack. So is 4 less than 10? Yes. So I'm going to return a 4. Now, if I return a 4 to here, notice that's going to possibly return quite a bit far down. So that 4, once it pops off the stack, is going to return me a 4, which goes back to 1410, which then just returns that 4. Okay. Gotta erase my stack here because I think I have more to go. Oops. Come on. Let me draw. Thank you. Okay, so next stack, I have 3710. Okay, so I need to draw myself a stack here. So M 37, 10. So 37, 10, they are not less than one another, right? So I got to call mystery 1 again. 37 minus 10 is 27. So I'm going to go mystery 27, 10. Okay, 27 is not less than 10, so I got to go again. So now this time I'm going to subtract 10 again. So 17, 10, right? Notice how I'm subtracting 10 every time. That's not going to help, so I need to subtract again. So I'll get 7, 10. So now 7 is in fact less than 10, so we're going to return X, which in this case at this time is 7. So I'm going to put a little over here. We're going to return 7. Now, since I returned 7, that 7's going to go in here. Notice this doesn't do anything except just return whatever mystery 7, comma 10 returned. So this guy is going to return a 7. This guy just returns whatever 17, comma 10 returns, which is a 7. And 3710 only returns whatever 2710 returns. So I'll return a 7. Okay, so here's what I'm going to ask you to do. I'm going to ask you to pause the video quick, and I'm going to ask you to try to see if you can get the other 2 figured out. So pause the video. See if you can figure out your answer. Okay, guessing you did. So this one you would get, I think it would be 0 is what you would get there, because you would get 8-2, right? And then 6-2, and then 4-2, and then 2-2. Oh, 2-2. Ha ha ha. So we actually get a 2 for that one, because 2 is not less than 2. Or no, 2 is not less than 2. Ha 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 ha. So 0-2. It'd be 0. There you go. I was right the first time. And then 50, comma 7, we would have 57, and then we would have 43, 7, and then we would have 36, 7, and then we would have 29, 7, and then we would have 22, 7, and then we would have 15, 7, and then we would have 8, 7, and then we'd have 1, 7, so we'd actually print a 1. That one took forever. That one was a long, 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 long time. Recursion's kind of fun, though. So sometimes it's kind of fun to play with, just because it's a lot of thinking. It's kind of like a puzzle. I almost imagine it like a shade that you're pulling down on a window. So you got to keep pulling it down, keep pulling it down, keep pulling down, keep pulling down. And once you reach the end, you get to like release it, and it just kind of kind of, rolls itself up as you get to watch it kind of go up. But with that, that is the end of this video. I will see you later, Sabers.